So I'll be talking today about knowledge graph embeddings and the knowledge graph platform we have, why we have it, to solve which problem, and how within that knowledge graph platform, how do we really leverage Elasticsearch to index, project the knowledge graph we have, and then use some of those projections to really perform some data similarity. So I'll start by introducing the concept of knowledge graph. So, and try to do it beyond the hype. So it's a kind of, how to say, since 2012, since Google release of their knowledge graph, it's basically everywhere. A new way or a new hype word, hype terms. So I'll try to give maybe a little bit more details about what we think, what we see as being knowledge graphs. So first, all the big players, they have a knowledge graph. They build a knowledge graph actually. So you have Google knowledge graph with these numbers, Facebook, Microsoft, LinkedIn. There is the Taste knowledge graph from Pinterest recently. You have Airbnb. You have they all have knowledge graph. So you can look this source if you want. It's written by people from this organization if you want more details. So it's just everywhere. And on industry, but there are open knowledge graph as well. You all know Wikipedia, so there is a knowledge graph counterpart, knowledge-based counterpart, which is Wikidata, where you can find many information about entities around the world, like people, president, regions, etc., etc. There are others, DBpedia, that are famous, Yago, many Freebase back then, a long time ago. So in industry and as well in general purpose public knowledge graphs. Because of that, the web just turned now into a giant graph, thanks to these many data that are exposed in a machine readable way. So this movement is called linked open data. So the web become a giant graph because of 5 characteristics of this way of organizing and sharing data in knowledge graph. The first one, well, it's on the web. The second is this machine readable data. It's not just web pages for people to read. It's if you take a Wikipedia page, you could have the counterpart in Wikidata, which is a machine readable form. So data for people and for machine. Non-proprietary format, open standard for everybody. And it's linked data because of they leverage the HTTP based ID, which is just the web infrastructure, to relate to things, to link things. So you, because of this 5 star, I would say, you end up with the web being a giant knowledge graph. Okay. So for example, UniProt, which is a biological data knowledge graph available on the web, it's about 55 billion triples. So it's just huge and just one of them. So first of all, why graph? Why not relational database? Why not file system? I say file system. Usually people say why file system. It's like a long time ago we have database, but some organizations still deal with file system. They're trying to move away from that because just the rise of the graph store. I think the last 5 years we witnessed just scalability in terms of graph storage. You heard about Neptune on Amazon, who brings property graphs and Sparkle graphs in a clustered way and scalable, Neo4j. Many other now that production ready knowledge graphs, graph store, I would say, with different data model, RDF triple store, property graphs. They are flexible and schemaless, like truly schemaless. You can add new node and relations without writing any schema, so that's really useful. And the ability to support a large spectrum of expressiveness. You can express more than just in an entity association model, like which is a relational database. So I'll give some example around that. So because of this characteristic, well, graph technology is ready to really being put into in production within organization to support various use cases. So deploying graph system in an organization require to change a little bit of thinking, to be more data-centric thinking rather than string or text thinking. So that's called thinking in graph. So for example, here I show some example. You move from string up to some entity which has an ID, John Doe, a bunch of attributes, its name, and then which is in relationship with another entity. Here, greet something which has a name, a pair file. Okay. So in a knowledge graph, the domain of application should be divided into entities which are identified, which are defined, described by attributes, and by relationship with other entity. So um, this is good because it's just a close to reality data model. The word is about things, which has quality attributes in relation to other things. And this way you can structure knowledge, you can structure data. So here I just give another example. So a knowledge graph is a graph. So graph node, relation, edge, etc. So I show here a particular point of view, which is RDF knowledge graph. So I will not talk about property graphs because those are other data. It's quite similar. There are some differences, so if you're interested, I could answer that. But in context of my organization, we use RDF knowledge graph for various reasons I'll talk about. So a knowledge graph can be seen here as a set of facts, set of statement, a set of triple. Okay, a fact is subject, predicate, object. So in a knowledge graph, every knowledge, everything is broken down into triple, into facts, into statement. Okay, so people usually don't believe it's possible, but it's possible. You can break everything into set of triples. Okay, so for example, here we have John Doe type person, grade type university. So these are type information. You have relationship between John Doe and the university. You have some attributes there, and it's kind of layered. Okay, it's a graph and it's a semantic as well because the expressiveness of what you can express. For example, if I take the 3 layers again, there is the conceptual layer, the one above, where you can categorize things. You can classify entities like type information, for example, and relate the classes by subclass of a class is more specific than the other. The layer in the middle, well, that's where the entity are the instances, which is John Doe, the EPFL University here, and you could have relationship between them, like affiliation here, for example. And the layer below, well, that's where the attributes are, which is the name, everything that is primitive type, string, etc. Okay. So thanks to this semantics, then you can run inference. For example, I give an example if grid here EPFL is a university and a university is of type university and it's known in the knowledge graph that university is an organization, then you can say that EPFL is an organization. Okay, because you have this sort of transitivity nature of the subclass of relation. So this is type of rule-based reasoning, I would say. So this is just an example of the expressiveness or what you can express and leverage in the knowledge graph. There are way many more. Okay, so it's a graph and it's a semantic. So the knowledge part comes because of the expressiveness. That's where the knowledge comes. So an RDF knowledge graph can be, the set of triples can be serialized in JSON, what we call JSON LD. So this is very important if you deploy a knowledge graph in an organization with developers around, because they don't like set of triples. Okay. I don't like set of triples. I'm a web developer. I'm a developer. I want to deal with JSON. I like it. So I want the JSON back. So there is a JSON serialization for this triple data format, which is called JSON LD. So JSON LD is JSON for linked data. So it was invented as a way to really preserve the semantics while exchanging JSON data to kind of cope with the ambiguity, etc. So it's just a JSON document with a bunch of reserved keywords like context. Context, for example, I put here schema.org. Who knows schema.org here? Yeah, so it's a common web scale vocabulary where terms are given IDs like places, people, organization, etc. And for example, we say context schema.org here, that means that name belongs to the namespace schema.org. We are not talking about any names. We are talking about the names as defined by schema.org. Okay, so this is just a way to give an ID to the JSON keys so that there is no ambiguity. Okay, and written like this, well, it's just a JSON document that you could put into Elasticsearch or in any other NoSQL database, and the developers are happy. Okay, so these two representations are quite equivalent. So this is the introduction for knowledge graph. Now, why in Bluebrain we are doing this? Okay, so that's the use case. So Bluebrain is a project for data-driven. It's a data-driven project to support brain modeling. So this means acquiring data, organizing data, preparing data, building models from the data, validating, refining the models, and then disseminating what you learn into through papers, etc. Okay, so that's the iterative cycle of the data-driven project. So as such, it's not that different from any other data science project. And this is an example of the type of workflow we have or type of information we capture in our knowledge graph. So typically, a scientist take a subject, run a brain slicing activity, and isolate a cell inside, and from that cell extract the shape of the cell and record the electrical activity of the cell. And these are two data sets, for example, that we have. And from the morphology and the EFIS recordings, they build a model. Okay, so this is just a simple example of the type of workflow and data entities I would say we have. So we have subject, brain slice, cell, bunch of activity, protocol, well, the scientists who perform the activity, software, etc. So these are entities in our knowledge graph that are described by properties, and they are related each other thanks to this type of arrows. Okay, and we do that for various reasons here. And the most important one is really to ensure attribution of all contributor. So that's the main reward. Is if you tell them if you do this, at the end of the day, you can click a button and get all the contributors right for the paper. They're all happy. Okay. So here I give a more complex example which deal with the simulation, which is again the data-driven cycle, which is really we wanted to have a system where the workflows, the systems react on data getting in the system, sort of notification system, push system, where there is a new morphology coming in. Well, okay, there is a workflow who listen, select, trigger a model, building a model from that trigger simulation, get back result, validate, and have this loop. So sort of continuous data integration and knowledge discovery. Okay, so this is our requirement. This is what we want to be able to do. So to do that, well, we needed a knowledge graph because it offers us a set of capability. First of all is to break data and vocabulary silos. So we are 130 people, completely different skills, cross-disciplinary. You have computer scientists, mathematician, physicists, biologists, neuroscientists. They deal with data that are completely different scale, etc. And we wanted something that could help us just organize the data, have a 360-degree view on the assets of the organization. Okay, the research data. So we have ETL processes that get this data from various formats, etc. Extract the entities clean, put in a knowledge graph. So that's the data integration layer, which act as a single source of truth for the research data. And we have validation capability. The interesting part for us was once we have this layer, well, all the clients, they don't need to have access to everything, to all the knowledge graph, okay? Because maybe they want a specialized view on top of the data, okay? Which require reading, transforming again, and shaping in different ways, etc. And that's where we come up with putting on top of our stack viewing capability, which is we have you take the knowledge graph, you extract some data, and you project into ElasticSearch indices, for example, or you project into another graph, which is a more specialized graph, etc. Okay, so that's what you call data integration and data disintegration for the different views. So this is typically just conceptually the type of stack we have, and of course this support various tasks. So I'll talk about now the our schema, because you have the knowledge graph, you have the infrastructure. I'll talk about that later. But if you want to break data and vocabulary silos, you need a schema. You need to speak at core level the same language. Okay, so we do have some schemas. So I'll go through them maybe quickly. So we call it knowledge graph schema. So it's a descriptor for the type of activities we care about. We use some schema.org, some specifications. So I'll pass quickly. And this is in a knowledge graph the type of pattern you could see. For example, this is morphology data here. And this is the whole business, scientific process, technical activities that led to the generation of that data. And this is the entities we store. So all of these are entities, activities, agent. So we can have data, images attached to it, etc., etc. So this is just a typical pattern for a given data that we have in our knowledge graph. Okay. So if I put them together, this is what we have. We have knowledge graph architecture, and then we have a knowledge graph schema to put everything in order and have the tools being able to go in cleanly, safely get data and know what to expect. Okay, so to do that, well, we build a technology called Blue Brain Nexus, which is a knowledge graph for data-driven science. It's open source, so anybody could go and get it. So it's Apache 2 license and use it as well. So it's a distributed system and streamed system. And we have a set of tutorials as well to test, and a sandbox people to test. I'll show the sandbox quickly. So I just show the architecture here so that you see where Elasticsearch fit here. So we have an infrastructure. So if I have the mouse, maybe I could just. So we deploy it in OpenShift and on premise in our cloud in house, but the sandbox is deployed in AWS. Okay. And so this is just the infrastructure, like the storage capability that we have. And then we operate 3 stores. So Cassandra as the primary store. So any entity you bring in the system gets stored here. And it gets projected into an Elasticsearch indices and then triple store indices, RDF triple store indices. Okay. So you have a document view and then you have the graph view at the same time. And the system makes sure that things are in sync. Any action, update, delete, addition here get propagated down here. So it's not 100% consistent, these two. This one is consistent, but not these two. So eventually consistent system. And on top of that, we operate 3 services. This is the knowledge graph where bringing entities and others happen. Admin for organization. Admin is where the organization and project are, and IAM is for security, ACLs, etc. And then we have a bunch of HTTP API, REST API, and a bunch of client on top of that. So inside KG, the data is bucketed through organization, and then project, and inside project you have data, schema, ontologies, protected by ACLs, and we use JSON LD as data exchange format. So this is typically what we have. So if I look closely to the views, so we have for Elasticsearch, for example, we have 2 views, like Elasticsearch, which is just, we expose just the search endpoint. So you don't have access to from outside to the right endpoints because the system manage it for you, I would say, but you could search and get results from that. And we have an aggregated Elasticsearch view, which is just a way, if you have all of these projects with each of them having an endpoint, you could have a sort of federation layer and target multiple of them in parallel and get back the result, combine them to send it back to the user. Okay, so this is typically how we organize the data. So we put in a big knowledge graph and we disintegrate into views powered, some of them by Elasticsearch. So I'll just show maybe the sandbox quickly. Yeah, less than 2 minutes. What we have. So sorry for my mini tabs. So you can log in using GitHub if you want. It supports GitHub connection. So yeah, I could come, pick one. So if you see, these are the organization. I could come get some project. Inside the project, I have some data, for example. And this listing is powered by Elasticsearch, for example. So get a list from Elasticsearch. What are the entities I have? And the entities, they have a bunch of types, and this is aggregation result. You know, you have this number of movie, this number of tag, this number of rating inside. You can check, do I have some data conform to a given schema? So let's say I just want to search movie 5, and then I could open it. Oh, some embeddings already. So I could see, well, it's developer point of view, so it's not what we show to our end users, the scientists at least. You could see the history, who did what, and a bunch of links towards other data maybe that are there. So anybody can go and use it, create your organization, bring your own data. It's private by default. Whatever you put in there is just, you're only going to see it, but we do wipe it quite sometimes. Okay. So this is typically how the data is stored and how you can interact with this. So let me go back quickly. So okay, so we have knowledge graph, we disintegrate. Now we have set of tasks. Okay, we need to use these things to perform some use cases, right? And one of them is content-based recommender. Okay, and for us, content-based recommender system is about similarity. Okay, because as you know, there are many flavor. you can group them by 2, basically. Collaborative filtering, if you have user rating, for example, or user data, or you just have data like typically you have in a knowledge graph, which is content-based filtering, which is really about building a vectorial, projecting the knowledge graph into a lower dimensional vector space. So for every node, you would have a vector space, and leveraging the dense vector type into Elasticsearch, and then being able to do cosine or whatever document similarity is there. The good thing with this is, if I show just here, is this is typically this is the pipeline we have, for example. So this is more the ETL part where the data is get ingested here, and upon ingestion, Nexus take care of indexing for you to into Elasticsearch that it manages. Okay, so that just remove the need for people to rewrite themselves the pipeline of getting the data and putting it in themselves into Elasticsearch. And we carry, do some preparation, train some embeddings for every node we get embeddings, and we put them back into Elasticsearch. Okay, and then we can carry those data through UI or put it some search interface, etc. Okay, so this is the pipeline we set up and we operate. Now it's written RDF to VEC, but that will not be RDF to VEC. So let me just, so I'll just quickly show what it looks like, these embeddings, and how you can just query quickly. So if I just come back, maybe I'll take back. So typically this is what we get. So this is 300 dimension. So it's done. Let me find it back. So I have a notebook explaining quickly. I'll not run training, don't worry. But this is going to be outside for everybody to use as well. So what we use here, where is it? Okay, so what I used for the training is you have different knowledge graph embeddings, RDF to VEC, not to VEC. RDF to VEC and not to VEC are, who is familiar with word to VEC? Just they take, yeah, it's just word to VEC, which is sequence of words, and they make a parallel into a knowledge graph. So they take a sequence of nodes, and the sequencing you build it thanks of given distance, some random work, etc. So, but it's the same algorithm, etc. Okay, but there are many others. For example, I'm using AmpliGraph, so it's an open source library that has a collection of knowledge graph embedding models that use TensorFlow, and that could read RDF and train and get the embeddings here. Okay, so let me just show. So I'll not run it. I train one. For example, I load a movie lens dataset. So if you come back to my data here, so I just ingested some of this data. So I'll just show for some movies. One of them. Okay, I guess this one. For movie 5, movie 9. So I'm trying to get the embedding. So this is just in memory embeddings. It's not what is in the system yet. So I have 2 of them, etc. Now what I want to demonstrate here is really how you can push these embeddings into the Elasticsearch using Nexus typically. So what we do is every entity you have, you can just add embedding property and just update it. For example, okay, need my token. Okay, sorry. Okay. So what I have done here is I updated the entities with embeddings in the system. So I just created an entity with an embedding in the system. I didn't say index into Elasticsearch. I just say, hey, knowledge graph, take. Well, this is an entity with embeddings, etc. So let's see the revision of the number. So it's revision 8. So I should see, if I come back to my data, that the movie 5.1. Okay, so pretty good. So that I have revision 8. So I get a new new data. So the good thing with Nexus is if I bring a new data, well, it picks it, and look, hey, do we have indexers that know how to deal with data? And then if yes, just hand it to that. So I'm going to show how to create such an indexer. So this is, so we can create an Elasticsearch view. So this is how you bring an Elasticsearch view. You do it on runtime. You don't need to redeploy your system. You can say, hey, create a new Elasticsearch indices in the knowledge graph, okay, out of the knowledge graph, and populate it with data that are of this type, or data that are not deprecated or deprecated, that include the Nexus metadata or not, and you can provide the mapping. Okay, so here I provide a mapping. You say, okay, embedding is a type dense vector, and I put the dimension. Okay, so if you inject this on runtime, let me just do this maybe. Okay. Okay, so I created one. So Nexus automatically starts saying, hey, I need to create a new Elasticsearch indices, and I need to populate it with data that match this criteria. Okay, so let's just have a look. So I could come, yeah, you could query the data like this and get both. So I could select the one I just created, and okay, let me try a bunch of results. Let me just maybe do it like this with 8. Okay, so I get back the data and the only movie 5, and then with the data in the index I just created, because it picked up the type and pushed them automatically according to the mapping. And you have the progression here. He's still running. You have 4% running. Okay. So this is how the, and any action you do on the data, he will ask again the indices, and they will pick up and they will index, etc. So this is typically how we get the embeddings into the Elasticsearch. And then it's a matter of really okay, where is it? Running just a regular, for example, script query here to compare with another embeddings, do a cosine with another embeddings, and get back the result. All right. Questions so far?
I suppose if I introduce a structured data, I receive an error, right? If I put a hello world in there, the machine would not say to that.
If you put it where?
Can you quickly kind of ask a question, repeat the question so it's also recorded?
Yeah. What?
Oh.
What if I'm asking what if I give to the machine like wrong data with the wrong structure? I suppose I receive an error, right?
Okay, so you're asking what happened if you
Yeah.
submit data with a wrong shape?
Yes.
Yes, you will get an error. Now you'll get an error at different stage, because we support pure JSON, so you can say, okay, I don't care about any schema, just get my data, and we have a default index Elasticsearch indices, which as well doesn't care. It will learn from the document anyway, so it will index it. But we do have a more controlled capability, like you can define your own schema. We use some shackle schema. When the data gets validated upon submission, if it's not okay, doesn't conform to what you expect, it will fail. Okay? Or in your indices, if you define the mapping, with all the mapping definition, well, of course, if there is a new data that doesn't conform to the mapping, well, it's going to fail, and you will get back the result from the Elasticsearch server. Okay. So the knowledge graph will mediate. Will just say, okay, give you back the. If it's a failure from the server, like if you have a server not available, there's a retry strategy. It will pause some time and retry. If it's a bad request or some client error, yeah, then you'll immediately get the answer. So there are some strategies of retry, so that always to keep in sync whatever is in the primary store with the different views, which is great for developers, because you don't want to be writing this boilerplate code. Okay. Question? Yes?
I saw a quick code is deprecated. Does that mean that I assume that if you deleted an experiment, this field would become true? What happens if you delete something? You realize that something you inserted is actually wrong when it's put in?
Okay, so that's a good question to, I think, to ask, if what happens if you delete something. First of all, you can't delete anything. You can deprecate. So the HTTP delete verb here corresponds to deprecate. So the system deprecate, that means that it will not show up in your search result. Just kind of disappear for the clients. But if the clients know the ID, always go and get it. You can always come and get it if you know the ID. Okay, exact ID. Just the HTTP based like this. Yeah, that ID here. Typically, if you know this, well, you'll always come and get it with the right metadata in the history, but it will not show up in any search unless the client really, really, really say only give me. I accept the deprecated ones, but usually clients, they just want the non-deprecated ones, and it will not show up in the count as well. So it has some incidence on the count. If you search something, the total is without those deprecated elements. We do that for audit purpose. We don't want to remove anything because we want things to be reproducible. It's a scientific process, etc. And but that's a very fair question for the management in long term. But that probably would be solved by archiving strategy at some point to really collect those and put them somewhere else, not in a hot storage, but in another place. Yep.
So it's deleted in Cassandra and then this is propagated?
No, it's not deleted even in Cassandra.
It's deprecated
yes.
in Cassandra and then this is propagated?
Yes. So that's really the design choice here is there is a single point of truth like the primary store because we have a journal. It's a journal-based system. It's akka. It's written in Scala, by the way, and it's akka, so it's a stream-based system. So, by the way, any project you can access the full journal through just HTTP. It's a server-sent event. You can come and just. It's not a notification system, but you could listen and see all the journals. Say there is a new entity being created by this person at this time. Oh, there is a new entity being deprecated by this person by this time. And you can react to those things. That's how the workflow react. Hey, I have new morphology. Should I do something? And then do something. So it's really the primary store really direct everything. So we can completely destroy our indices and we can recreate them from scratch because the journal is being just like a bank account, just replayed with snapshots. So that's fast, but it's replayed. So you could delete all the indices. It will take some time, depending on the data size, but you will get back your indices. And that's the good thing here. Right. So I'll just add that this is like we have this pipeline, we set it up, and we are experimenting with different knowledge graph embeddings strategy to see really what is the best. But the mechanic and the pipeline is the same, and yeah. Right. So I'll put the notebook out so that you have access. 40%.
How long does it take to rebuild everything from scratch?
Wow. Well, I have here, just give you an idea how many movies do we have. You see how slow. We have 9. Well, this is the movie lens dataset, so we have 9,000 something. It depends on the setup. I would say in our production environment, I would say these type of things like it's a matter of minutes. But again, right now I think we have around less than 2 million entities. So if you delete everything, it takes 2 hours, half a day, something like that, because we don't have many entities. But we have a benchmark on documentation as well with I think 100 million 20 entities, which is some billions triple somewhere. It's performed quite decently. Now I think people are okay they accept that the data is there, they could go and access it, but maybe the indices take a little bit time. Usually tell them, okay, take holidays and come back, everything will be fine. Yep, excellent.
Thank you very much.
Thanks.